Ever noticed how once you learn how to ride a bike, learning another two-wheeler seems effortless? Here's the kicker. AI models can do the same. Transfer learning gives AI the same head start. So it skips straight to winning. Let's see how. Welcome to AI Club Pro, where we make AI concepts feel like everyday ideas. Today, we are unpacking transfer learning, the trick that lets AI models borrow knowledge instead of starting from scratch. In this video, you'll learn what transfer learning is and why it's a game changer for deep learning. We'll also learn the difference between three different types of transfer learning techniques. We'll also look at how we can adapt a pre-trained model for your own dataset even if you don't have a lot of compute or examples in your dataset. We'll also look at what some of the common pitfalls are that to look out for and how you can make sure that your model actually improves in its performance. So let's get started. Imagine you have learned to ride a bicycle. Later, picking up a motorcycle feels easier because you have mastered the balance and steering aspects of it. Transfer learning works the same way, but for AI. Instead of training a model entirely from scratch, you build on what it has already learned. As a result of this, the model does not have to rediscover the basic patterns. Typically, training a deep neural network model requires millions of examples. But when you use transfer learning, you can get away with a few hundred or a few thousand examples. So essentially, you'll need less data. You can also lower the cost in terms of both time and compute because you're not having to use as much data and you're not having to train from scratch. So, the core idea of transfer learning has roughly three stages. The first stage is the pre training stage, where you essentially take a large model and a huge data set, something generic, which could have, for example, millions of images, or in case of natural language, billions of words, and then you train it on something generic. So that's the pre training stage. Then comes the knowledge transfer stage, where you take that model with all its layers, where it may have learned something useful. Like in case of images, it may have learned features like edges, shapes, relationship between edges, etc. And in case of natural language, it may have learned things like word patterns, grammar, relationship between different words, gender, etc. So during knowledge transfer, you take these learned features and then apply it to a completely new but related task. The third stage of transfer learning is where you adjust the model just enough so that it becomes an expert at the specific problem that you're trying to solve. Transfer learning in general is applicable to several different domains, like image classification, text processing, or audio processing, etc. However, for ease of understanding, since it's easier to understand visual stuff, we are going to take images as an example to explain how all of this works together. So let's assume that we have a large network. Let's use ResNet 18 as an example. So you can see that this network has 18 layers, beautiful residual connections, convolution filters in each layer, and all the bells and whistles of a robust model that performs really well. Note that this has approximately 11.69 million model parameters. And if you're not sure about what model parameters mean and why they're important, please check out our video on what is an AI model. A model with so many parameters occupies approximately 44.79 megabytes on your hard drive. And typically, when you train a model, it is empty. This means that the model parameters are not populated with any numbers. Only after the training process is complete, the model is populated with values of these model parameters. Let's assume that this model has been trained to classify 1000 categories of images. This means that it's a classification model that classifies an input image into one of 1000 categories. To train this model from scratch, it will take a couple of days or weeks depending on the hardware that you're using. So now let's assume that someone did this hard work for you of making a highly performant model on some random 1000 categories already. This is the pre-training part of the transfer learning approach. This model is called the pre-trained model. So where can you find these pre-trained models? So typically there are different repositories from where you can download these models. For text, Hugging Face is a good repository. For images, depending on the implementation, let's say you go with TensorFlow, there are these pre-trained models available in Keras. So really depending on your modality, you will find standard pre-trained models that you can simply download and use. Somewhat like learning a bicycle, where you learn to balance, to steer as your core skills. In this case, the network has learned some fundamental aspects about images, like edges with different orientations, corners, relationship between these edges, different shapes, etc. As you go deeper into the layers, more sophisticated aspects about the image are learned from the model parameters. This is something that is done once, and then transfer learning is about reusing this knowledge over and over again for different tasks, which may or may not have anything in common with the images that this model was originally trained on. Knowledge transfer is about applying the basic knowledge that this model already has to your new task instead of starting from scratch. There are three main approaches in how you could do this. The first one is feature extraction, where you take the pre trained network and freeze all the layers. Freezing means that you make no changes to the model parameters. You remove the top layer, which is the prediction layer, and then add your own new layers on top of it. Then you train this classifier to learn the model parameters associated with the new layer alone. For example, I can take the pre-trained ResNet 18 network and decide to do a binary classification on an MRI image to see if there is a tumor or not in an image. In that case, I would add a final layer with a binary classifier in this case, whose parameters are learned by training the network. Note that the entire network is frozen, except the layers that are added by you. This makes the number of learnable parameters quite small, reducing the time and compute needed for training. This approach works when we have little data, a small amount of data, and want a quick baseline. The second approach is to fine-tune the entire or a part of the network. So instead of freezing all the layers like we did in the previous approach, we can decide to freeze only a part of the network or not freeze anything at all. You're still starting with a good initialization since it's a pre-trained network, but then you let the entire network learn and adjust its model weights along with the new layers that you may have added. This is a good approach when you have a moderate amount of data and require high accuracy. The third approach is called domain adaptation, which is more complex and something you use when your data is very different from the data that the model has pre trained itself on. For example, The model was trained on natural images, and your data consists of spectroscopy images. In this case, you could add tricks like extra regularization or specialized layers to bridge the difference between the source and the target data. We used images as an example to demonstrate how transfer learning works. Transfer learning, however, can be used in text, for example, using a BERT model trained on vast amounts of Wikipedia data to conduct customer sentiment analysis on a small, where you have a small review data set. Or in case of speech, you could use a voice model that is trained on standard English, and then you want to adapt it to regional accents by fine tuning on a few hours of labeled data. So, transfer learning is a neat trick that helps with speeding up your training process. However, there are a few pitfalls to be aware of. If your new task is too different compared to your pre-trained task, the pre-trained layers may mislead rather than help. This means that the basic features that the pre-trained network has learned are not useful for the task that you have in mind. In such a case, it may be a better idea to start from scratch if you have enough data. Another pitfall is overfitting, where when you fine tune on a tiny data set, the model can kind of memorize it, as a result of which you'll see that the model has a great performance on the training data, but then when you test it on a data set that it has not seen before, it doesn't perform that well. So that can happen, and that's called overfitting. And typically, to counter that, you can add something called a regularization layer or do early stopping. The third issue that can happen is architecture mismatch. This can happen when you're doing domain adaptation. So you can't graft layers from a completely different model or a family of models without careful adjustments, which is to say that you can't simply take a layer or several layers from one model and then plug it into another model without making a few adjustments. If you don't do the adjustments, then you will encounter problems like dimension mismatch or incompatible operation types, etc. So you have to make these adjustments when you are picking layers from different types of models to create your own architecture, but then you're also retaining the model weights. So, in summary, transfer learning lets you build on an existing AI model's experience instead of training from scratch. This saves you time, data, and compute. There are several different approaches in how you can do this, which include feature extraction, fine tuning, and domain adaptation. I hope this helps you with making transfer learning less mysterious. Thank you for watching, and if you have questions or topic ideas, leave them in the comments. Don't forget to like, subscribe, and ring the bell for more clear practical AI breakdowns.